So today we're pleased to have Garrett Summers joining us. He's a California native, as I understand it, who was an undergrad at UC San Diego before moving to Ohio State. He's been doing his PhD work with Mark Pinsino. And so he's going to tell us about some of that work and the impact of rotation in star spots on significant stellar evolution. So,
all right, thank you. Thank you for having me out. It's been a lot of fun this morning. This is the first time I've given a talk on this subject at an institution, so I'm delighted to do it. And so, as was mentioned, the main subject of my talk here is going to be the impact of rotation and star spots on evolution of young stars. And so before I get into talking about what these two effects actually do to the evolution and observables of these stars, I'll just motivate a bit why we might care about that. So there's a number of astrophysical timescales which are constrained by the ages of young stars. Particular ones of interest are the star formation rate. So for instance, or rather the rate of star formation within a specific molecular cloud. So for instance, if you go look at a young open cluster and you notice that it has an age spread, in other words, stars that were born from the same cloud were born, say, 5 million years apart, then that tells you something about the efficiency of star formation. You know, it would have taken maybe several dynamical times to form it. Whereas if in a young cluster you have essentially no age spread, then star formation is going to be very efficient. So you want to be able to understand the ages of individual stars in young clusters to be able to constrain the star formation in that fashion. So the timescales of accretion are constrained in similar ways, where if you look at a young cluster, and you know what its age is, and you know what percentage of its stars are accreting objects, and then you look at a bunch of those clusters over a series of ages, then you can understand how accretion dies down with time. Similarly, planet formation theories are constrained by the ages of young stars because planets form in protoplanetary disks which surround stars during their early lifetimes. These disks dissipate after a few million years, so in order to build giant planets with large gaseous envelopes, you need to basically form the planets before that disk disperses. And so measuring the lifetimes of these disks offers a strong constraint on the allowed time for planet formation. And finally, another interesting thing to do with pre-main sequence stars is if you can accurately measure their masses, you can constrain the stellar initial mass function. And young clusters are a great place to do this because stars haven't yet gone through their evolutionary lifetimes and died, which makes studying the IMF in older populations quite difficult because you've lost a lot of your older mass stars. So pre-main sequence clusters and the stars within them are used for all these different applications. But one thing you'll notice is that in each of these I've talked about specifically masses and ages, and how masses and ages are quite important to accurately measure in these stars in order to use them for these applications. So the rest of this talk is going to be about how these masses and ages are measured, or rather how the non-standard stellar physics affects the way that they're measured. So first, before I talk about rotation and star spots as a possible complication to these mass and age measurements, I'll talk a bit about the standard stellar model, which is how these masses and ages are measured by most studies. So the standard stellar model is a culmination of about a century or more of work in trying to understand the structure and the evolution of the sun and other stars very much like the sun. Essentially every evolutionary track you would have ever seen published in a paper is a standard stellar model, and it takes in a number of relevant physical effects for stars like opacities and equation of state and various things, and allows you to calculate the evolution of that star throughout its lifetime. Now there's a core assumption of standard stellar models that I'm going to bring your attention to, which is down here on the bottom, which is that there are 3 parameters which the standard stellar model assumes uniquely determines everything about the star. That is the mass, the composition, and the age. So when you start a standard stellar model evolutionary track, you set its composition, you set its mass, and it just evolves and does its thing from then on. And no additional physics that can differ between stars impacts their lifetimes. So this is a very simplistic viewpoint. That being said, it's still been extremely successful in a lot of regimes. So just to illustrate that, I plotted here the color magnitude diagrams of 2 different globular clusters. You can see the stars here sort of on the lower main sequence, subgiant branch turnoff in the beginning of the giant branch. And along with that is plotted a standard stellar model, which as you can see does an exquisite job of predicting everything about that track. Again, you see another one over here, which again very accurately predicts the evolution, or rather the structure of this cluster And right here are basically the only parameters that went into making this line. So as I said, the age, and these are composition parameters, hydrogen, alpha elements, and iron abundance. And then, of course, mass is the final parameter, which controls where along this line you lie. So as you can see, it's extremely successful at predicting what these open clusters look like. So I'm not here to bury standard stellar models. I'm simply here to point out that they are not necessarily applicable in all regimes.
Was the helium abundance fit obtained by fitting, or was that assumed to be open to?
In this case, it was almost certainly fit to the cluster itself. Yes. Because helium, turns out, is quite difficult to measure in stars. So the alpha and Fe were probably measured, and then the helium was what was used to basically figure out the parameters of the cluster. So standard stellar models, as you can see, have been extremely successful in certain regimes, but they simply just don't apply to all regimes of stellar evolution. And so I'm going to point out a few different places where these standard stellar models are not able to accurately predict the intrinsic parameters of stars. So one is when you try to use them to measure the radii of very rapidly rotating active stars. So this plot here shows a series of data points, which are masses and radii taken from eclipsing binaries. Mass here on the x-axis, and on the y-axis is the percentage of their radius that is larger than predicted from a standard stellar model. So this black line here is basically a mass-radius relationship normalized to if all of the stars were correctly following the standard stellar model predictions. What you see is that essentially all of them lie up above these predictions here. Now there's this other line here, this red line, which represents an older population. So this black line was zero-age main sequence, but stars during their lifetimes increase in their radii. And so anything with a reasonable age could fall somewhere inside this shaded red region and could be explained by standard stellar models. Now, some of these eclipsing binaries do. There's this group here and these ones over here. But more than half of the stars from this particular catalog here are way too large. They have too inflated radii to be explained just by their mass and by their composition and by their age. So the one thing that's hinting what might be going on here, I mentioned that these are active stars. That's because all of these particular eclipsing binaries are very short period, 2 or 3 days at maximum. And when you have very short period binaries, the stars are tidally synchronized together and they rotate at that rotation rate for their entire lives. So stars would normally spin down and at, say, 10 gigayears would be spinning at something closer to the rotation rate of the sun, which is quite slow. It's like 25 days, whereas these things may actually, even though they're quite old, be rotating at a few-day period. And that's why I believe that that's a hint as to why they are not accurately predicted by standard stellar models. So anomalous radii of active stars is one outstanding problem with standard stellar models. Another arises when you look at the lithium abundances of young open clusters. So this is a lithium pattern from this open cluster called the Pleiades, which is a little over 100 million years old. And each of these gray points here represents an individual star within this cluster. Now, the reason lithium is an interesting element to study is because it has this property where it's very fragile and gets burned in the interiors of stars, in the deep interiors near the core, but is not quite fragile enough to be burned at the surface. During the pre-main sequence, as stars are contracting down onto the main sequence, essentially, their surface convection zone reaches very deep into the star, and the base of it is hot enough to actually burn lithium. But then once they reach the main sequence, this convection zone retreats and in a sense freezes out that abundance for many megayears after that. So with standard stellar models, because mass and composition and age are supposed to uniquely determine their structure, you predict that all stars of a given mass in an open cluster should have exactly the same lithium abundance at fixed age. And that's what this red line here represents. This is a standard prediction for what was expected when people went to go look at the lithium pattern of this cluster. And keep in mind that this is a logarithmic scale here, so it's quite clear that, and the error bars are maybe a few tenths of a dex at most on some of these, so there's a huge discrepancy here. In particular, you can get something like a 2 order of magnitude spread in lithium abundance at fixed temperature, which is more or less fixed mass in a cluster like this, which is just completely unpredicted by these standard stellar models. Now again, a hint as to what might be going on can be gleaned from looking at rotation rates. In this particular plot, the size of the points represents the rotation. So these big stars up here are rapidly rotating, and these small stars are slowly rotating. So what you notice is in particularly this regime right here, there's a very strong correlation between rotation rate and lithium abundance, in the sense that fast spinning stars are more abundant. So again, that's a hint that physics that's not included in the standard stellar models, which include, standard stellar models don't include things like rotation and magnetism, and so this is a hint that maybe it's one of these additional physical effects neglected in standard stellar models that's causing this effect. So finally,
I'm amazed how at 4,500 or between it and 5,000, how bimodal the distribution is if the dot size is a measure of the rotation speed. Is that really the fact?
Yeah, it's really quite striking. So if you were to fit, if you fit a line to say things rotating faster than 2 days, which I think was the cut that I used for this particular plot, and things rotating faster, they're just totally different sequences. I mean, you do have a few objects. So for instance, there's this one right here. There's one up here. So there are a few that seem to sort of go against this general pattern, but in general, it's quite striking and is definitely real.
How large is the arrow bar in temperature?
Those will be closer to 50 or 100 Kelvin. So one final property I'll bring to your mind that disagrees with standard stellar models are the colors of some young rapid rotators. So again, this is the same open cluster as right before, the Pleiades, and I'm now showing a color magnitude diagram in V minus K versus V, and these points here represent stars. So again, these small points are slow rotators, and the big circles are rapid rotators. And what you see is that there's a differentiation in this plane where the rapid rotators appear to be systematically redder than the slow rotators.
And you said that these fast rotators are because they're in binaries that are close.
Okay. So, yeah, not necessarily. So these are just young stars, so they're rapid rotators. So this sample is the same as the previous plot with lithium, but it's not the same sample as the eclipsing binary radii that I showed in the first plot.
Should we think of them, redder or brighter?
I believe it's redder.
Okay.
So I'll come back to why I think that this is going on.
So in the last slide, we had temperature. There was a question about temperature uncertainty V over V minus K, and the ones that are cooler are also redder. So is that a problem with the V minus K temperature relation? Were those temperatures on the previous plot determined by color or by some other means?
So they were determined by color, but I took steps in this previous plot to account for this effect. I could talk to you afterwards about what I did. I won't get into it now. But some of this effect may, in fact, be going on in this plot as well, but this is still a real dispersion at fixed mass for sure. So radii of stars, their lithium abundances, and colors in certain planes, for when you have these rapid rotators, appear to be different from what you expect from these standard models, which are generally calibrated on older stars. So the common theme in all three of these instances I brought up, again, is rapid rotation or magnetic activity. And it's maybe not too surprising that these are actually causing problems compared to our standard predictions, because standard stellar models were designed for stable, quiet stars like the sun, and not for highly active stars like things that are 100 million years old. Now, some solar physicists might object to me saying that the sun is quiet, but it's, of course, a relative term compared to pre-main sequence stars, so I think I'm justified in saying it. And to demonstrate just how much more quiet, I've plotted here a magnetogram of the sun, and you see these sort of blotchy black and white areas, which correspond to star spots in white light. They're basically portions where the magnetic fields are poking through the surface and changing the temperature at that specific location. And what you see is that they cover a pretty small fraction of the solar surface. There's one here, one here, one here. But if you integrate it over the entire disk, it's never more than about 1% of the surface of the sun is covered in spots. On the other hand, you have some young stars. So for instance, this one here, V347 PEG, which is a nearby pre-main sequence star. And I plotted a magnetogram of this. Obviously, the resolution is not going to be quite as good. But the color map here on the star itself is showing essentially the same sort of polarized areas like this. And what you see is this red region is massive. So you can think of that as a giant star spot that is on the surface of this star. Now, some stars have been claimed to have spot covering fractions of something like 30 to 50% of their surface have areas, regions that we normally think of as these small spots on the sun. In some young active stars, they cover almost half of the star. So it's not surprising at all that this would do something weird to, say, the radius. If you take, a star which has a certain luminosity and you cool the surface by a massive amount, it's going to have to expand to basically maintain flux conservation. It might also do something weird to the colors. You now have, different temperature zones on the surface. So it's not that surprising that these would be, you would find these problems with standard stellar models when you look to young active stars. And so just to be slightly more quantitative about how different, I mean when I say active versus inactive, I'm showing a plot here from this paper. This bottom axis here is rotation period. And the y-axis is the average surface magnetic field strength. Now the sun are these two black points over here. So you see that it's rotating out here at about 25 days and has surface field strengths of something like a few Gauss. And the two different points represent the solar cycle. So where the sun is in its 11-year cycle will determine exactly what the average magnetic field strength is, and it varies between those points. Now the sort of stars that I'm talking about are way here on the other side, rotating maybe faster than a day period. As you can see, their surface field strengths can be quite a bit more, something like 500, or in some cases even maybe 1,000 Gauss. So very, very different, 2 orders of magnitude different compared to sort of the maximum that the sun can get. So, and again, you can see there's this quite strong correlation between rotation period and magnetic activity, which is again maybe telling you why these stars that are rapidly rotating are the ones that are showing anomalies in, say, their radius, because the magnetic activity correlates with the rotation rate. So motivated by all of these features of the empirical stellar pattern, I wanted to see if we could basically improve upon the standard stellar models by incorporating the effects of rotation, incorporating the effects of magnetic activity in star spots, and reconcile these anomalies. So my plan here for how I progress to do this is, first, I just wanted to see if I took essentially a toy model of a star and I inflated it to match basically the radii that you see in those, shown in those eclipsing binary plot before, mass versus radius, and see what this does to the lithium abundance. Now I thought, okay, this might allow you to create a spread in lithium for the following reason. If you puff a star up, you're going to cool it not only at the surface, but throughout the interior. And in particular, you're going to cool it at the location where lithium destruction is most efficient. Now, lithium burning is one of these nuclear reactions that's extremely temperature sensitive. It goes something like T to the 20. So even a 10% change in the radius would maybe correspond to a 10% change at the temperature in some inner location of the star, and could massively suppress your lithium depletion rate because of the temperature sensitivity of the reaction rate. So once that's done, so that will be step 1. And then I will show what happens when you include the effects of rotation. Because rotation not only leads to magnetic activity, but it drives another effect called mixing, which I talked about a bit this morning at tea. But the basic idea is that when a star is rotating and develops strong internal differential rotation, where the core is rotating faster than the surface, this will, through hydrodynamic mechanisms, drive material from the inside to the surface of the star. And so if your inner material is depleted in lithium and you then drive it to the surface, you're going to dilute the surface convection zone and reduce your observed abundance. And so you need to take that effect into account. And then finally, I'll include in these standard stellar models a treatment for how star spots should impact the conditions at the surface and the flux transport conditions in the interior, and see what that does to the models. And that will kind of bring everything together. So first, just as I mentioned, I'm going to look at some toy models of inflated radii. So basically, I won't get into the details of how I did this, but I tweaked some of the parameters in a standard stellar model, which dictates the efficiency of convection. And by changing this parameter, you're able to model the impacts of magnetic fields threaded through the convection zone, and leads to an inflated radius. So in this left panel here, I show mass. So these are a series of models, and radius inflation percentage that's driven by this parameter tweaking I was talking about. Now this red line represents just a standard stellar model, so obviously it's not inflated at all compared to itself. But these other models which have the tweaked parameter reach inflation percentages of something like 10 to 15%, which is sort of the same order of magnitude as what's implied by the eclipsing binary data that I showed earlier. So if you now take these models and follow their lithium abundance as a function of time, and you compare it now to the Pleiades data, these are the same data points that I showed before for lithium, what you see is that these models that are indeed more inflated were cooled in the interior and can suppress the rate of lithium destruction by an enormous amount, by enough that you get 2 orders of magnitude difference at fixed temperature. So this is an encouraging hint that if some physical effect is able to basically cause stars of equal mass and age to have different radii during the pre-main sequence, then this fan of lithium abundances that was previously unexplained would naturally be produced. So that's an encouraging first step. But as I mentioned, rotation is a complicating factor because it drives this mixing. And it works in the way that more rapidly rotating stars should be more depleted in their lithium. But this is, of course, the opposite of what I've shown you in the Pleiades. The rapid rotating stars are more abundant, whereas if it was only mixing that was occurring, they should be more depleted because they've driven more material from their core, more lithium-depleted material from the core into the surface. So you have to simultaneously account for both radius inflation and for rotation. So just to illustrate what I just said, I first ran models that only included this rotational mixing effect and had no inflation at all. And I got the following pattern. So this here shows, again, the same empirical lithium pattern. The rapid rotators are here, the slow rotators are here, and these lines here just are meant to represent sort of the approximate envelope of all the data to guide the eye. And on the right, I show a synthetic pattern, which was run basically a series of evolutionary models that were run from the initial conditions needed to produce the rotation and temperature pattern seen here. So I basically took this data and estimated what initial rotation rate and mass were needed to produce the rotation rates and temperatures seen here, and evolved it forward just looking at rotational mixing. And what you see is basically what I had mentioned, that this rotational mixing causes the rapid rotators to be more depleted than the slow rotators. And you get this pattern, which is an inverted, is inverted compared to the empirical pattern. So what this says is that rotational mixing cannot be the only effect that is affecting lithium depletion on the pre-main sequence. In other words, you need to somehow make these rapid rotators suppress their lithium depletion. And as
Can you say a word more about the convection or how we model it? Are we still at the mixing length simplification?
Yes.
Or much more sophisticated?
No, so at the moment it's a mixing length simplification, that's right. So I'll make it slightly more sophisticated when I talk about star spots, but yeah, so this previous plot was just, yeah, exactly. So I was saying parameter, but yes, mixing length is what I changed. So if you don't have any sort of radius inflation at all and you only consider rotational mixing, then you get totally the wrong answer. So then I said, okay, well, what if these rapid rotators are actually magnetically active or have star spots, and that causes them to be puffed up relative to the slow rotators? So I basically took the same models and I, again, altered the mixing length on these rapid rotators, and this is the pattern that emerges. So now you see that these rapid rotators do, in fact, because of their radius inflation, appear significantly more abundant than the slow rotators, and the size of basically the dispersion more or less matches the empirical pattern, and you also get the correct sign of the lithium rotation correlation. So this was even more encouraging than the previous plot because it shows that if you can now argue that that some mechanism causes rapid rotators to be puffed up relative to slow rotators, then rotational mixing is not a problem for explaining this particular pattern.
Can you be more specific? So you changed the mixing length parameter from what to what?
So I started out with a solar calibration, which just in number is about 1.8 or 1.9. And then, so I guess I can go back to this plot to show that. So this was the solar calibrated one at 1.9. This one here is more like 1, which leads to a change in radius, as you can see. It's mass dependent, but it's something like 5 to 10%. So you can think of these things here as being inflated by about 10% relative to the slow rotators. So I keep saying inflated, and I was talking about mixing length, but really that's sort of a simplification, and you really like to know what actually causes this radius inflation. So as I said in my title, I'm going to argue that it's star spots. So this is a beautiful picture here of, I guess, a sunspot, not a star spot. There are these cooled regions on the surfaces of stars. Magnetic fields are threading out of them adding additional pressure support at the surface, and therefore the gas pressure doesn't have to carry as much of the load and can be cooler. That's essentially the reason that star spots are cooler. And you see that it can be quite a striking difference between the photosphere, which is up here, and this. I think that oftentimes the temperature difference can be something like, the spot will be about 70% of the temperature as the surface itself. And so I won't get into the details of how I did this. You can ask me afterwards if you're interested, but my advisor and I took into account how these star spots impact the transport of flux near the surfaces of stars. This involved both treating the flux transport in the convection zone and right at the surface, how it affects the pressure. And I'll just jump right to the answer here. And so this shows basically what these star spots do to the fundamental parameters of our stellar models. So first I'll bring your attention to this right here, which is the parameters that I adopted for these particular spots. 50% spot coverage is a quite extreme number, but it's sort of consistent with the upper envelope of what's observed in young open clusters. And again, I said I chose 80% temperature difference here, which is sort of characteristic of what people often see. I said 70% a second ago. Some people say 70, some people say 80. In this particular paper, I did 80% difference. And so these lines now show how this spot coverage changes the fundamental parameters of these stars at the zero age main sequence. Particularly the radius is puffed up. There's an interesting structure here to it, which if you're interested in, you can ask me about later, but I think that it's actually real. But in general, the radius increases for all of your stars. The temperature, surface temperature, average surface temperature decreases, which isn't too surprising because you're taking a star and putting a bunch of cool spots on it. And the luminosity also gets decreased by a significant amount, especially for low mass stars. Now, the reason that it's more efficient in the low mass stars is because as you go towards lower masses, you have deeper and deeper convection zones, and spots are predominantly a convective property of convection zones. They don't appear in radiative zones. So if you have a convection zone that's close to your nuclear burning core or the location where you generate a lot of your energy, then that's going to have a bigger impact on your luminosity. So basically the spots are directly cooling the interior of the star where energy generation is going on. But for the moment, I'm just going to talk about this R at first. So now we can go back to these anomalous properties of these young active stars and see how these spot models change our interpretation. So here's this plot again showing all these eclipsing binaries which cannot be explained by the standard stellar models even at 10 gigayears. But if you now include spot effects, you essentially increase the size of this envelope and encapsulate all the data. Now, as I mentioned, except for this one, but I think that's a subgiant, so I would ignore that one. And as I mentioned earlier, the reason that I think it's fair to keep both spot and age effects for these objects is because they're all short period eclipsing binaries and are rapidly rotating even if they're quite old. Normally, you wouldn't think a star at 10 gigayears could rotate at enough to have 50% spot coverage, but some objects that are stuck at rotating rapidly might still be able to show both age effects and spot effects. So in any case, spots appear to do quite a good job of predicting where this upper envelope would lie, so I think that's quite encouraging. Looking now to the Pleiades lithium pattern, you see that here was the standard stellar model, and it sort of tracks the lower envelope of this pattern, but can't actually predict this significant range. And then if you now include your spot models, they're puffed up, cooled in the interior, and so the lithium depletion is significantly suppressed. And again, this was not a fit to the lithium data, it was a fit to the upper envelope of the spot properties that are observed. So the fact that it matches pretty well with the actual dispersion, I think is quite nice. And also makes a very solid prediction that these stars up here, these rapidly rotating stars, on the pre-main sequence should be more heavily spotted than the slower rotating stars. So I think that makes a very testable prediction.
I'm still puzzling over something. If really these binaries they are locked, the rotation is locked to the orbital motion, so they must no longer be spherical, they must be pretty tidally deformed, and there must be all kinds of additional complications, no?
I would say that's almost certainly true for the very, very close ones. There have to be departures from spherical symmetry, but a lot of that is also just driven by the rotation itself. Rapidly rotating objects do deviate from spherical symmetry, and that does actually, it's one of the mechanisms that drives mixing and drives angular momentum. So I think that's true. So I didn't take that into account in my models.
I would have thought it could be the dominant effect. I mean, even the moon at 60 Earth radii, is slightly elongated, but this gets very strong when you get to 2-day orbital period.
So the dominant effect for what?
Well, I would just somehow then guess that there are temperature variations across the surface that's basically egg-shaped or something like that, elongated, and that must compete or be a separate effect.
Oh, okay, so you're saying that that's the dominant effect that's causing this radius effect. Yeah, so I mean, people have looked at that, but I think that even if you look at the most rapidly rotating stars, that the radius effect doesn't appear to be caused by the rotation rate. I think that's right.
In the spots, how do you assign temperatures? No, the next one.
Oh, in the next one?
Right, so basically the stellar models now are, there's multiple different black bodies on the surface
Mhm.
of the star, both observationally and the models here. So how did, what was it?
Right, so that's a good question. So what I actually did, yeah, so that was sort of asked earlier as well. So what I actually did was you can take, normally you might take, say, B minus V or something and get a color from it. But what I did is took colors from different, basically different bands, so B minus V, V minus I minus K. And if you take all of these together, you can do a much better job of pinning down where the peak of the blackbody function is and assigning a temperature. So in a sense, it's an average of temperatures derived from different bands whose effects are shown to sort of cancel out, is what I did.
Doesn't your model now change what the effective temperature of these stars with spots should be?
Yes, so that's true. So these stars here, I guess in my scenario, they're not exactly at, so they are at this temperature in a sense, but they're not at the mass that would normally be assigned to that temperature in a standard model. So I think that's right. So that they are not only their lithium abundance is perturbed upwards because of their inflation, but they're cooler as well. So it's not exactly a one-to-one mass if you go this way, but it's a small enough effect that this dispersion is still real.
Isn't the effective temperature, the temperature of a black body, in the same radius and luminosity?
Yeah, so in a sense, you have these effects that give you some radius and you have some luminosity. And so then the effective temperature is basically just derived from those two in the way you can think about it. But it's still well defined even for a heavily spotted star as long as you have a radius and a luminosity. Okay, and so then finally, this was the third anomalous feature that I showed. You have these rapid rotators which appear to be red relative to the slow rotators, and it's not just that they're wrong compared to the models, but they're actually different compared to stars in the same cluster at the same age with different rotation rates. And so now if you take these spotted models, not only are they have slightly lower effective temperature, but they also have these dark blotches on the surface which basically change the black body emission, or rather the weighted black body emission across the whole surface. And you can put these effects into the model and you see that in the V minus K band, they do indeed move to lower temperatures. Now, it's not exactly a perfect match here, I will admit. It does pretty well down here, but there's still some difference between the rapidly rotating stars in our models here. I think this might be indicating that this sort of two-zone temperature model that I've assumed is too simplistic. Because if you actually look at spotted stars, spots themselves are not a single temperature. They have two different zones, the penumbral and umbral regions, which are at different temperatures. They also have, they emit more short wavelength emission. They have these faculae regions, which emit a lot of things in, say, B band. And so I think a simple two-zone model isn't quite sophisticated enough to really predict these colors, but I would say that this is encouraging that you do find a lower temperature for these rapid rotators. All right, so I think spots, I hope that I've convinced you that spots do a pretty good job of explaining each of these anomalous features, but you might ask me, what's the significance? So what can you actually do with this? So one thing that I've identified that I think is a quite important consequence of this investigation is that spots will significantly bias your measurements of young stellar parameters. Now, in some sense, it's obvious why this would work, or why this would happen. If you have spots on the surface, you change the effective temperature, you change the luminosity, and so if you use standard models which don't take into account these effects, then you're going to misidentify the mass and the age of a star. So to illustrate exactly how this works, I'm showing here a theoretician HR diagram, so effective temperature and and luminosity, and 2 different isochrones, which is essentially a series of masses at one age, which in this case is 3 million years, calculated from my evolutionary code. Now the red line itself includes no spots, so you can think of these as a standard stellar model, and the blue line is this heavily spotted case that I was investigating in the previous several plots. Now if you focus right on this black X here, say we went to a young cluster and we found a star that was lying right there. Say we have a distance, we have an SED, we have everything. So we do know exactly what its luminosity is and exactly where its effective temperature is, and it just lives there on the HR diagram. Now, what people would normally do to measure its mass and its age would be to put down these evolutionary tracks, which I show here, they're sort of faded out, and these isochrones, and say, okay, well this X is right at half a solar mass and is right at 3 million years because it lies on this red line, and so that's the mass and the age that you get. However, if this star is actually a heavily spotted object, then you do not want to be using these models to actually derive their parameters. You want to use spotted models, things that take into account this additional effect. And in particular, you'd want to use, say, these blue models here. So if you find the evolutionary track for these heavily spotted object that runs through this point, it's actually a 0.75 solar mass track, and the actual age is 8 million years. And you can see that from the fact that it's sort of down below this 3 million year isochrone. The star has actually contracted farther than you think. And so if you compare this to the answers that you got when you just used your standard models, you see that the mass is wrong by about 50%, and the age is wrong by almost a factor of 3. So this can be quite a significant effect. If you try to interpret the mass and age of heavily spotted objects using standard stellar models, you'll get erroneously low masses and erroneously low ages. And this could be a strong systematic effect in a lot of young clusters if star spots are as ubiquitous as people think in many of these young clusters.
But if this was a sort of stochastic thing with stars, and maybe it isn't, maybe they all sort of behave the same, but if there really was two populations, that would make the HR diagrams look very ratty, wouldn't it? I mean, with the main sequence down there at the terminal.
So it would make them look quite ratty, and as it turns out, pre-main sequence HR diagrams are quite ratty. And there's a few different...
Where you're wrong when I got the mass by factor of 2.
Yes, I think so. So there's various effects that could actually cause this that people talk about. One are if you have age spreads within clusters, then you're obviously not going to have a single isochrone. You're going to have some dispersion. There are non-uniform extinction in these star-forming regions because a lot of these stars are still basically embedded in their parental molecular clouds, and so that can also mess you up. There's a whole bunch of observational problems that make these young cluster CMDs messy, and I'm proposing one more.
And the reason you might get a very different spot area, you could do that at a given mass, is simply the initial rotation of the star?
Yes, so that's what I'm arguing in this paper, that the rotation rate is the driving factor between this. And I think that the evidence for that in my argument is basically the lithium pattern, where you see that the abundant stars are the most rapidly rotating. A pattern like that, a pattern like that is almost impossible to create, or at least nobody else has come up with a way to create that without non-uniform radii, basically on the pre-main sequence driven by rotation.
But it's a legacy of the sort of random variations in angular momentum that have not been carried off by any magnetic.
Right.
So they stay like that for a long time. Well, we're not talking that long, I guess.
Right, so the age at which this lithium pattern seen in the Pleiades would be imprinted is something like 5 to 10 million years old. So certainly it's at a point when the stars are close to peak rotation rate. So if this is in fact a real phenomenon that's occurring, there's a number of important implications that this has. So the first I sort of alluded to in this previous discussion, which is that this will create a spurious age spread from a coeval population if you have different basically spot filling factors between stars of the same mass in a young cluster. So to test the magnitude or to test how severe of a problem this would be, I went back to my lithium pattern here, and I said, so if it's true that spots are causing this dispersion, then the location of each of these stars in this fan here tells you something about how spotted it was when it was young. So these things down here can't have been that spotted, but these things up here had to have been heavily spotted. So you can then come up with a distribution of spot properties as a function of mass that must have existed from about 5 to 10 million years. You can then model that population and say, what would I have gotten if I used my standard stellar models to derive the masses and ages of those stars at 10 million years? And the result is this right panel here. So on the bottom here, I show mass versus age. These blue points represent my backwards modeled Pleiades, all to 10 million years. And the red points represent the masses and ages that you infer from them. As you can see, the dispersion is quite large in age. Some of these most extreme objects, you would have said they were about 3 million years, when in fact they were 10 million years. And so this could imprint a spurious age spread into a young cluster. And this would be an important effect for, as I was talking about, star formation studies, because if you have age spreads in young clusters, it means that star formation must be somewhat inefficient, and it takes, say, several dynamical times of the cloud to actually form everything into stars, whereas if you have no age spread, then it means that the star formation had to have been extremely efficient. And so this is a potential false positive for age spreads in young clusters. And you'll note also that there's a mass bias here. So some of these objects, you basically get the mass right, but then down here at the low mass regime, you're sort of under-predicting the masses of all these objects. So for studies for the initial mass function of open clusters, this could also be quite a significant effect. It could give you a spuriously bottom-heavy IMF. So I think that these are two applications where this could be quite an important effect to take into consideration. Now, a few other implications are, there's a few other implications I'll discuss. One is constraining the timescales of planet formation. So planets form in these protoplanetary disks which surround stars when they're young. This is the now famous HL Tau image from ALMA. And you see these gaps here, which are presumably planets that are starting to accrete material from their surroundings. Now, the timescale over which this accretion onto planets occurs is still uncertain. So people will run models of planet formation and try to figure out how quickly it takes to build planets. For lower mass stars, something like less than 0.5 solar masses, people argue that you need at least 10 to the 7 years to actually create a core that's large enough to accrete a big envelope and build giant planets. On the other hand, empirical studies of the lifetimes of circumstellar disks find that they live at most maybe about 6 million years. There's a mismatch between the lifetimes of circumstellar disks or protoplanetary disks and the time to build planets. Now, if all of these stars were actually older than you thought by maybe something like a factor of 2, then the lifetimes of disks that are inferred now are spuriously low by about a factor of 2. So I would argue that if you go back and systematically reanalyze nearby young open clusters, basically these open clusters, which are the ones that are used to set this disk dispersal timescale, you might find that if you include the effects of spots, all of them are in fact older than previously thought, and as a consequence, these disks can survive significantly longer than previously thought. And this could reconcile this difference between empirical studies of disk lifetimes and planet formation.
Are you doing this?
Yes, this is what I'm proposing to do. So, right on that question. So the next steps after having discovered this potential effect is I'd like to first go search for a lithium rotation correlation on the pre-main sequence. So I said that this pattern should start to emerge right around 10 million years. Well, K2 is currently observing some clusters that are right about 10 million years old, and I've seen some preliminary data, and there's a hint that there is a correlation between rotation and lithium that's forming even that early. So that would be quite exciting, and I think could be a smoking gun that that this lithium pattern in the Pleiades sets in right around that time scale, or right around that age. So that would be the first step. And then once you do that, you can place good constraints on the range of spot properties that exist in these young clusters. Now you can place some of those already based on the Pleiades data, as I showed in that previous plot, but you would want to do this it would be even better to do this right at the age at which this dispersion is occurring, or at which the dispersion is creating the lithium dispersion. So that would be the second step. And once you've done that, you can then go through and reanalyze the young cluster ages and reanalyze this time scale of star formation. You can probe for true intercluster age dispersions and set some limits on the efficiency of star formation. reassess the protoplanetary disk dispersal time and see how that compares to predictions for the timescales of planet formation. And finally, you can also constrain the accretion timescale, because that's another parameter so accretion in the early lifetimes of stars builds up their masses until they're, reach basically their final parental mass. And the timescale over which that occurs is understood entirely from the ages of young clusters. So by reanalyzing those ages, you may be able to set new limits on accretion timescales as well. So just to reiterate my conclusions, magnetic activity and rotation have a significant influence on the structure and evolution of young stars. Rotation, lithium, and radius data collectively imply that during the pre-main sequence, stars of equal mass and age are physically different. And so standard stellar models are therefore insufficient to explain their evolution and to explain observable features of their patterns. And finally, the masses and ages of spotted stars are systematically underestimated if you use unspotted evolutionary tracks to derive their parameters. And future directions that I'd like to go is to quantify this total impact in actual nearby open clusters and see how that impacts the cluster age scale, and look at implications for things like protoplanetary disk survival time. All right, thank you.
So I think I want to try to reiterate or something what you did, just so I understand. So the effect of spots, you had an empirical idea of how spotted stars are, et cetera, and you used that actually to constrain the surface boundary condition of the stellar model. Isn't that right?
Yes.
Then you change the mixing length prescription all through the star. Now, the mixing length is really presumably being changed by some magnetic effect that you don't really know what it is. You don't have a model for that. It's really complicated.
So I would say
you
that
need some assumption, I think, about how the magnetic effect changes the structure of the star, which is just the simplest one of saying the mixing length every year changed like.
So that's not actually quite what it was. So when I was talking about the mixing length, that was my, here I can go back. That was sort of my initial steps just when I was trying to see if this was a path that was worth pursuing. So here I was messing with the mixing length as just a toy model for magnetic activity. I used those same mixing length models for this step as well. But then, I guess I should have mentioned this, when I got to my star spot models, I used only the star spots to influence the structure of the star. I now used a solar calibrated mixing length for all of my star spot models. So I did not alter the mixing length for this portion.
So in your star spot model, then the only thing that was changed was the surface boundary condition?
The surface boundary condition and also the flux transport in the convective region. Because basically the way that I was thinking about it is, if you have these spots on your surface, the flux that would normally have been traversing through, say, that column gets diverted into the unspotted regions. And so in your evolutionary code, you need to account for that by essentially ramping up the radiative energy transport in the convection zone in the unspotted regions. Then at the surface itself, basically you account for the pressure, the change in the pressure due to all this magnetic activity. And those were sort of the two main things that were changed in the code. So for the star spot models, there was no change to the mixing length. I should have been more clear about that.
Okay, but then you made a somewhat different assumption about radiative transport through the star. And then essentially the best justification maybe for that assumption being as simple as whatever you made. Because it could have been, I think, more complex if the magnetic structure was in some different set of layers than the convective transported at some level. Who knows? Is that the lithium abundance actually sort of comes out. The lithium abundance is purely predictive from your model.
That's right.
So if it agrees, that's a sign at least that your assumptions about how you slightly arbitrarily change the stellar model sort of did the right thing. Is that?
I mean, I think I agree with that. I think the fact that that each of these different anomalous features is sort of explained by, I mean, I don't think it was quite arbitrary the way that we chose to do the spots. I think that it's under the constraints of a one-dimensional evolution code, it is true that you're not going to be able to do everything as perfectly as in, say a hydrodynamic calculation. But the method that we chose, I think, does a reasonably good job of modeling the way that the flux is redistributed. So I don't think it's entirely arbitrary. But then I agree with you, I think the fact that it reproduces the lithium pattern in particular suggests that we're on the right track.
You're generally talking about rotation rate as a proxy for when these effects start becoming strong, right?
Mm-hmm.
But if you think it's also magnetically connected, another parameter you might want to look at, or maybe you already have, is like the convective Rossby number, the ratio of the convective overturn time scale to the rotation period. Because usually you want that near unity if you want dynamos to operate.
Right.
Have you, or do people compare against that to see if it gives you, if it's more representative of whether you have a sensitivity?
So certainly it's true that the Rossby numbers are very low for all of these pre-main sequence objects. They're all probably less than 0.1 in that case. So they're all definitely in a regime where the dynamo would be active. One thing that I want to do to improve upon these models is explicitly link the spot properties to the Rossby number. So at the moment, I'm saying I choose 50% of the surface to be covered in spots, and that's just what it is. And I think that because I'm only looking over relatively short pre-main sequence timescales, that's maybe okay to set limits on these effects.
Yeah.
But you're right that what you really want to do is to tie it to, the rotation rate and the convective overturn timescale. And so that's something that I'm looking at.
Because that could change. The convective overturn time scale could change quite a bit along this mass sequence.
Yeah, so that would also, it would cause both changes in the spot properties as a function of age and also as a function of mass.
Any other questions? All right, let's thank Garrett again.
Thank you.